Saxon Advanced Mathematics, Lesson 12. Our topic at the beginning of the lesson is about angles and diagonals in polygons. We already know something about this. We know that there are things called interior angles. They're the angles on the inside of a polygon. And we know with specific regard to a triangle that if you add up these interior measures, the sum of those angles will always be 180 degrees. That's a very useful piece of information. So what if we had the same kind of information about some other polygons? So I'm drawing a 4-sided, 5-sided, and 6-sided polygons to help us figure out the pattern. The easiest way to determine the sum of the measure of the interior angles of a polygon is to pick one of the corners, known as a vertex, and make sure that there is a line from this point to every other vertex in the shape. From here to here, we already have a line. It's one of the outside walls. We add one there. And then from here to here, we already have a line. So we can see very easily that this quadrilateral is made up of 2 triangles. So it's the sum of the measures of its interior angles will be 2 times 180 or 360 degrees. Let's try the pentagon. Again, I picked this one. This is the easiest way for me to visualize it, but you can do the same exercise from any one of these vertices. I like to put dots on them to help me key in on where the vertices are. From here to here, there's already a line. We add one there, we add one there, and then there's already a line there. We see that this shape is composed of 3 triangles. So we multiply 3 times 180, and we get 540 degrees. And we'll do it one more time with a hexagon. Beefing up my corners so I can see them really well. That already exists. One there, one there, one there, and then that already exists. 1, 2, 3, 4 triangles. 4 times 180 equals 720. So we can do this with any shape. We can draw it out, and we can draw the basic shape, we can create the diagonals, we can count the triangles. Another way to do it that's a little bit quicker is that the number of triangles that you get will always be equal to the number of sides minus 2. Okay, so for a triangle, it is 3 minus 2, so that's 1 triangle. For a quadrilateral, it's 4 sides minus 2, so that tells us that it's 2 triangles. For a pentagon, you see I'm just rehashing this, it's 5 minus 2, 3 triangles, that's what we got. See, these all match up. And then for a hex, that has 6 sides, so 6 minus 2 equals 4, and that's what we got there. So if you have a 32-sided object, you don't have to figure out how to draw that. You can just use this quick little formula. And you barely even have to memorize this, because I always just think, oh, a triangle has 1 triangle and 3 sides, so 3 minus 2 equals 1. There's the basic formula. I remember you subtract 2. Okay, this is all true for interior angles. That's what we've been talking about. Angles that fall within the shape. Of the polygon. But there are also things called exterior angles. We don't really talk too much about those. That's because they're super simple. The interior angles, there's lots more drama with those. Let's pick any crazy polygon we want. Let me start by making it easier. I'm going to keep that there. But let me start with just a simple triangle shape to talk about what an exterior angle even is. If we visually extend any one of the lines of the triangle, we create what's called an exterior angle. It falls on the outside of the triangle. What's interesting about these is that they're very easy to measure, because if we just take this and find its supplement, subtract it from 180, then we know our exterior angle. So they're quite easy to work with. Same thing, let's see, we wanted to find this one. Just extend the line, and if you know this, subtract it from 180, and you can find it. So exterior angles, and they can form in either direction, right? They can form in either direction, but when we're trying to add them up, we would just calculate one for each side of the triangle. So let me just draw another picture where we don't confuse it. If we were trying to find the sum of the exterior angles, we would extend this line once, and we would extend this line once, and we would extend that line once. Okay, so each line gets extended once. We would add those up and see what we get, right? The sum of the measure of the exterior angles. But here's what's cool about them. Imagine this. Here's you and me. Let's do it together. Okay? We're gonna measure the sum of all these angles. Oh, this isn't true though. This one's wrong because it's concave. It has to be convex only. So we're gonna start here, and we're gonna walk around this shape, measuring the exterior angles as we go. When we get back, we will have walked in a full circle, right? We went around measuring everything like this. So that tells us that the sum of the exterior measures of any convex polygon will always be 360 degrees. And you can remember this by simply imagining yourself, and with me if you want, walking around that shape. The angles will always add up to 360 because that's how far we walk as we go all the way around them. So the sum of the exterior angles of any polygon will always be 360. All right, so let's use this in a cute little problem. And it's really our only problem for this lesson. Find the sum of the measures of A, the interior angles, and B, the exterior angles of a 7-sided convex polygon. Okay, 7 sides, that's important for finding the interior. Convex, that's important for finding the exterior. Let's take them in order. If it's a 7-sided object, then we know that to find the sum of the measure of the interior angles, we have to figure out how many triangles are in it. We could draw a picture and draw in those diagonals. I'm not opposed to that. I don't consider that a bad strategy at all, but I'm going to do it the other way. 7 minus 2 equals 5 triangles. Must make this up, and I multiply 180 degrees per triangle times the 5, and I get 900 degrees as the answer for part A, and that's correct. Okay, I just remembered that little formula, and honestly, I didn't even have to memorize it because I just go, okay, a triangle has 1 triangle, so it's 3 minus 2. Number of sides minus 2. Okay, now I go over here and I'm thinking about the exterior angles, the sum of the measure of the exterior angles, and I imagine myself walking around the outside. I need to make sure that it's convex. It is. If it was concave, this little automatic answer would not apply, but it is convex, and so my answer is 360. Yay, beautiful. Okay, that concludes our conversation about angles and diagonals for today. And now what I want you to do is put down your pencil or whatever you're writing with, sit back and relax, and let me show you something about proofs that I want you to see. Am I going to ask you to duplicate this? Honestly, I don't think there are any problems that require this of you. It's kind of a fun exercise in just talking about how proofs work and what they're good for. And I will walk you through it. I want you to just relax, not worry about copying everything down. I want you to see if you can follow my train of thought. If you can't, don't worry about it. If you can, cool. Just I want that to give you a little bit more confidence in proofs and what they're good for. What we want to do is prove something that we've talked about. We've said that the measure of an inscribed angle equals half the intercepted arc. I'm going to write that down. Again, I will say, you don't need to write down what I'm doing for the rest of the lesson. You can just watch it. If you want to write it, you can, if you think that would be interesting or fun. But don't worry about doing that. Okay, so what we can do is take a look at a circle. We're starting with an inscribed angle that happens to be a diameter also. It goes straight through the middle of the circle. And the other piece of it, we have drawn so that it actually falls just touching it like that. Imagine that this is on a hinge. We can take this and we can bring this up if we want to make it more of a classic inscribed angle, but we've chosen to push it all the way down so that it makes a right angle right here. Okay, so this line goes through the diameter, and this line is actually a perpendicular. It's a tangent, if you will, right? Because it's perpendicular here. It just touches our circle at one point, and I'm going to put some letters on this just to help us keep our bearings. All right. We know in this that these two lines are perpendicular because we know that a tangent is always perpendicular to the radius that intersects the tangent, right? That is a postulate. And then this piece we know is just straight on from there. So we can say that this angle, angle BAC, equals 100. No, it equals 90 degrees, sorry. Right? It's a right angle, so it must equal 90 degrees. We also can see that this piece of it, and that is arc BXA, that's half the circle, so we know by definition that that is 180 degrees. So what we have done by use of what this is called the chord tangent theorem is we have proved that an inscribed angle is half of its intercepted arc, because we can say that angle BAC equals arc BXA divided by 2. This doesn't follow a fancy format, but it is a simple mental process of showing that if we take an inscribed angle, here, let me just draw it. Let's say our inscribed angle started like that, where this one goes through the diameter and this one's just up here, looking a little bit more like a proper Teenage Mutant Ninja Turtle. He's just looking up toward the sky, isn't he? If these were on a hinge and we took this one that's more to the right and just pushed it down, so it got to this point, we would have this picture. So this is just a wonky inscribed angle, just kind of an extreme one. All right, and so that's how we can prove it. We know that this is a 90-degree angle because that's what happens when you have a tangent intersect a chord like that. And then we know that this is 180 degrees because it's half a circle. So that's how we can teach you something like this, John and I. We can tell you this and ask you to trust us, but we can also back it up with evidence and a proof. If you're interested, I'm not going to go into this because it's too confusing. We can also take this basic information, this basic mode of thinking, and we can prove, see, this is what we just looked at, where these two form a right angle. We can extend our proof to cover angles that are larger than this original 90-degree angle, and we can do it for angles that are smaller than 90 degrees. So we can refine that. I don't want to put that into your head now because I don't want to confuse it. I want you on a really strong footing with this picture. But this diagram and the proof mind process, thinking process that we just discussed, that proves what we've been saying, that the measure of an inscribed angle is equal to 1/2 of the measure of its intercepted arc. This chord tangent theorem proves it. Okay, that's all I want to say on this. There are 2 examples that I'm not working that have to do with the fine tuning of this for the larger angle and the smaller angle, which they just involve adding a section and subtracting a section. Let's not even talk about that. But I believe that there are no homework problems that address I'm just glancing to make sure. There are no homework problems that address this chord tangent theorem. You don't have to use this in a homework problem. The main reason I'm showing it to you is I want you to know that when John and I give you a piece of information like that, there's always a proof to back it up. And that with a little bit of exploration, you guys have all the tools you need to understand how those proofs work, even if we don't take the time to put them in the homework and have you create them yourself. All right, that's all I have to say about lesson 12. Thank you very much. I will talk to you soon. Goodbye.